is that I start with an ab initio description, much like Sayori does. I use a slightly different method. The method I use is called no-course shell model, but it's the same idea. You start with a chiral effective field theory-based interaction, which is somewhat grounded in terms of a description of quarks and gluons. Throw that into my many-body method, and I get out wave functions and other observables that I can predict. Now, Sayori showed some really nice results and predictions of different values. And so ab initio methods are really great for predictions, but the values that we get out don't necessarily have immediately a very intuitive picture to go along with it. And so what I'm trying to do is use the ab initio predictions to look for or map onto simpler pictures that are easier and more intuitive to understand. And so today I'll be mapping on the ab initio results onto two of the sort of simplest pictures I can come up with. One is the sort of effective single particle model, like the shell model, and the other is sort of on the opposite end of the spectrum where you sort of assume everything's collective, which is the Elliott SU3 model. So before I jump into results, I'll briefly review the ab initio method that I use, and then I will jump into two different case studies for beryllium and carbon. Specifically, I'll be looking at the neutron-rich beryllium and carbon isotopes, some of which we heard about a little bit yesterday. Okay, so the no-course shell model in a nutshell, like Sayori said, we're trying to solve the Schrodinger many-body problem, and the way you do it in the no-course shell model is you're expanding your wave functions in some basis, and this turns my eigen problem into a matrix eigen problem, which theoretically I can solve just by diagonalizing the Hamiltonian matrix. The basis that I use is called the harmonic oscillator basis, which I'm sure many of you are familiar with. But this is where the basis states are configurations, which are distributions of particles over harmonic oscillator shells, or Slater determinants. And the states in this basis are organized by number of oscillator quanta above the lowest Pauli allowed configuration. So for beryllium-8, the lowest Pauli allowed configuration has 2 protons and 2 neutrons in the n equals 0 shell, and 2 protons and 2 neutrons in the n equals 1 shell. This is what I call n excitation equals 0, or 0 excitation quanta. In the no-core shell model, we don't have any kind of inert core, so if I want to have a configuration with 2 excitation quanta, I can either promote 1 particle by 2 quanta, or 2 particles each by 1 quanta, and those particles can either come from the valence or from the filled shells. So this is the fundamental difference between this method and the shell model. So I organize my basis states by different number of excitation quanta, and then I try to solve the eigen problem in this basis. I can't use the infinite dimensional basis, so I have to truncate the basis, and I do this by saying, I'm going to take all configurations with excitation quanta up to some parameter which I call n max. Of course, then the question is, what value of n max do I use? And so what we do is we look for what we call convergence. So what's shown here is the binding energy of beryllium-10 plotted versus h bar omega. H bar omega is a basis parameter length scale associated with the harmonic oscillator. If I have gone to high enough n max, then my results will stop changing as I increase the size of my basis, that is, as I increase the value of n max. So these curves are different values of n max, so n max equals 4, 6, 8, 10, and 12. And as you go up in n max, the curves are getting closer and closer together. Once they start to fall on top of each other, this signals convergence. So what you're seeing here is that as you go from 10 to 12, there's a very small change, so it's approaching convergence but not yet converged. Similarly, you would expect it to be completely independent of my choice of basis or choice of h bar omega parameter. So as I go up in n max and increase my model space size, the curves should start flattening out as they are here. Again, not quite converged because they're not quite flat yet, but they're getting there. You can see similar behavior patterns this is the proton radius for beryllium-10, again plotted versus h bar omega with the different curves for different n max. You can see by n max 12, the curve is starting to flatten out, and for certain values of h bar omega, they're quite close together. Again, they're starting to trend towards convergence, particularly in this region, but it still has a little ways to go before I would say it's a truly converged result. So then, okay, why don't I just go to higher n max? Well, the problem is that this basis is very large. So at Nmax 12 for beryllium-10, you're looking at a basis size that's a little over 10 to the 10. So I have a 10 to the 10 by 10 to the 10 matrix that I'm trying to put on my supercomputer, and that's about as large of a matrix as I can fit into memory on the computers I have access to. So that's about as far as I can go for beryllium-10. So the results aren't perfectly converged for these isotopes, but that doesn't mean we can't still learn something from them, because a lot of the properties are sort of starting to be in place at this point. So I wouldn't claim precision predictions at this point, but sort of the bulk properties of the states are starting to come into play. So the first picture that I want to look at is the, I call effective single particle picture. So when you talk about single particle states, they're not really a physical concept, they're more of a mathematical concept, and there's lots of different ways to choose your single particle states. One choice, of course, is just the harmonic oscillator single particle states. My experimental colleagues prefer using Wood-Saxon. Here I'm using what's called the natural orbitals, and this is where obtained by taking and calculating the one-body densities for my wave functions, and then diagonalizing that one-body density matrix. The reason I do this is that it's the orbitals which are going to maximize the occupation in the lowest lying orbitals, which for me is going to be the most shell model-like configurations. But it is a choice. So what's shown here are the occupations for beryllium, one of the beryllium isotopes. These are the proton orbitals. They correspond to the shell model orbitals. They're in that same order, so you have your 0 s a half, your 0p 3/2, 1/2, and so on, going up. In the p shell nuclei, even though the s is shown here above the d in the p shell nuclei, it's sort of understood experimentally as well as theoretically that the s orbital is actually lower in energy, which is why it's plotted in this order here. And I can then do my calculation, extract out my single particle states and the occupations that go along with them. Each of the different boxes here corresponds to a state that I can put a particle into. So you have almost 2 particles in the 0 s a half, and 1.5 particles in the 0p 3/2, and about half a particle in the 0p a half. So I can look at this for across the beryllium isotopes. Again, these are the proton orbitals, and across all of the isotopes that I'm looking at in beryllium, the proton occupations are pretty similar, which is not surprising given that beryllium isotopes have a well-known 2-alpha cluster structure. So your protons are basically sitting in your alpha clusters, or at least that's what this is suggesting. What's more interesting is to look at the neutron occupations. And as you go up in number of neutrons, you can see that the particles are starting to be added in and filling up the different shells. But if we focus in on beryllium-10, you can see that while you do have the pretty much filled 0 s a half, the p 3/2 shell is not really full. In fact, you have almost a lot of probability sitting in that 1p a half. So shell model would say, well, this isn't quite right. You should have filled up the 0p 3/2 orbital first. And in fact, you expect that there to be a n equals 6 subshell closure there. And that's consistent with actually what we see in terms of the binding energy of beryllium-10. You do see a bit of a drop as you supposedly are filling up that orbital, but that's not what we're seeing here. This is maybe actually not that surprising when you consider the fact that the beryllium isotopes are quite deformed. So what's shown here is the proton deformation on the top and the neutron deformation on the bottom. I want you to focus in on the filled symbols. So there's different ways you can try to get at the deformation. The filled symbols correspond to what is the deformation extracted using what I call the Q invariant method, which is where you take the matrix elements of the Q.Q operator. Because this is a rotational scalar, you would expect that the expectation value of Q.Q in the lab frame would be equal to the matrix element of Q0, which is the intrinsic quadrupole moment dotted with itself in the intrinsic frame. And so you can then extract out an intrinsic quadrupole moment that then allows you to calculate beta. The open symbols are a different way of doing this. It's if you assume a good symmetric rotational picture. There are ways that you can then extract out the intrinsic quadrupole moment from the spectroscopic quadrupole moments. In theory, if it was truly a good symmetric rigid rotor, the values would fall on top of each other. Obviously they don't here. These are light nuclei, they're not exactly rigid rotors. But for a lot of them, you see quite a bit of consistency, even though the values are different, except for perhaps beryllium-10, where there's actually quite a large gap between the two different types of deformation. Regardless, whichever method you choose, you have a deformation that's roughly sitting around beta equals 1. So instead of talking about a spherical sort of shell model or single particle picture, perhaps the Nielsen model is a better way to look at this. So Nielsen model I took here is just a Wood-Saxon Hamiltonian to get the if beta equals 0 or no deformation energies, and then you add on your deformation term in the sort of Nielsen-like Hamiltonian, and these are the sort of energies that you get out. What happens when you add in deformation is you no longer have rotational symmetry, you no longer have good angular momentum, and so these different orbitals or occupations that you can then start putting your particles in won't have good J, they do have good M sub J, and these lines will then actually be, for example, this blue dashed line, which is in the P3 halves, coming from the P3 halves orbital, will be some linear combination of P3 halves plus the P1 half, because they both have sub J equals a half. And then if I then do a naive filling at about beta equals 1, start putting particles into my Nielsen orbitals, and then look at what the occupations map back onto in my sort of natural orbitals picture, the natural orbitals occupations are indicated by the white stripes with a little bit of gray shading overlaid on the natural orbitals calculation. And it looks pretty good for the protons. And not quite as good, but still somewhat decent. You still see some expectation of having a little bit of that 0p a half, and this is for beryllium-10. Now I did pick just sort of a random, just average beta for all the beryllium isotopes, and we saw earlier that there's something a little funny going on with beryllium-10, and at the end I'll come back to that, maybe what's going on there a little bit. But it's really not too bad, and if I look at all of the occupations across all of the beryllium isotopes I looked at, for a very naive, back of the envelope type of calculation where I just sort of threw in beta equals 1 and used textbook values for the Wood-Saxon Hamiltonian, it actually looks pretty consistent with what I'm getting out of the ab initio results. Now, there's one case where this does not look good. In beryllium-12, I've got significantly more occupation coming out of the ab initio results in the 0p a half than I am expecting from a Nielsen picture. But this can actually be understood from the fact that beryllium-12 is a bit more complicated, and it has to do with the fact that the ground state is actually what would be called an intruder state in the shell model sort of picture, where you would have, and so what's happening is when you have these sort of intruders, low-lying intruder states, especially when they become the ground state, there's often going to be another low-lying state that corresponds to the sort of the normal shell model type looking state, and that's what we have here. You have these two low-lying 0+ states, and these states are mixing. And it's this mixing that's causing the issues with the sort of occupation picture. So what I'm showing here is the absolute energies calculated for the two different 0+ states in beryllium-12 with Nmax. The filled symbols are what comes straight out of the ab initio calculation, and the open symbols are if you sort of assume two-state mixing, you can extract out the unmixed energies. And what you can see is that as you go up in Nmax, what eventually becomes the ground state starts out higher in energy, crosses the state that ends up being the excited state, and as they come close in energy, you get level repulsion pushing the energies apart. They start moving further apart. It starts to unmix, and it continues down. But we're fairly confident that the states are close enough to convergence in our calculations that, at least in our calculations, they're not going to completely unmix. And in terms of experimental data, you also don't expect them to completely unmix because there is a measurable E0 transition, which in the absence of mixing, given the states have very different structure, if they weren't mixed, the E0 transition should be about 0. So in terms of what's going on, sort of a shell model type picture, the reason we call it intruder is the preponderance of the probability of the wave function is projecting onto configurations with 2 excitation quanta or higher for the ground state. And you actually have a much larger contribution coming from configurations with zero excitation quanta for that excited state. Now there is mixing. If this wasn't mixed, and I don't have the results in this talk, but you can actually see that when you unmix, there's no nx equals 0 contribution to the unmixed intruder state at all. So what's happening then in terms of the occupations is you would have unmixed, you would have expected the 0p half of the excited state to be more or less full, and the fact that it's not is because it's mixing, and that's why you get this little bit of a discrepancy going on in terms of the Nielsen picture. Doesn't completely solve it, but it does make it look a lot better. And then because there's a lot of talk about halo nuclei, I just wanted to draw your attention to, as you go from beryllium-10 to beryllium-11, it looks very much like you took beryllium-10 and put a particle where most of the particle went into a 1s1/2 state and a little bit into a d5 halves. So looks more or less what you'd sort of naively expect for a halo state. And I can also calculate the radius to just sort of confirm. And if this is the proton radius, the triangles are the calculated values, the green lines are experimental values. So we've got not perfect, but decent agreement with the proton radius. And as you can see, there's a very large jump in the neutron radius between beryllium-10 and beryllium-11, which you'd expect for a halo nucleus. So it's fairly consistent. Okay, let's sort of play the same game with the carbon isotopes. So again, you have your proton occupations, which are red, and the neutron occupations, which are blue. And as you go up and start adding particles into the different orbitals in the neutrons, surprisingly, this actually looks even more shell model-ish than the beryllium isotopes. And in fact, when you get to carbon-14, it looks like you in fact do have a n=8 shell closure, which you did not see in the beryllium isotopes because you had that intruder ground state. And it's more or less full as you go to carbon-14. It becomes more Nielsen-ish like as you continue up in terms of the neutrons, and you start to see these sort of split occupations going up as you go up from 15 to 16, 17, and so on. And just as with the beryllium isotopes, I can calculate beta. This is just the beta calculated with the Q-invariant method. Here you're seeing that both the proton and the neutron deformation of the carbon isotopes is a bit smaller than in the beryllium isotopes. The proton is hovering around 0.9. It's very constant across all of these nuclei. But you see a little bit of staggering movement in the neutrons, which are kind of fluctuating between 0.6 and 0.8 here. So I can again sort of play my same game with take the Nielsen model and then go around 0.7-ish and take a look at how it maps onto my occupations. And it does seemingly even better job with the carbon isotopes than it did with the beryllium isotopes. The proton occupations are pretty well consistent. The proton occupations are the same pretty much all the way up the carbon chain. So here you've got 12, 13, and 14. 12's a little off, 13, 14, pretty decent. And continuing up, it's really a pretty good description of what we're seeing in terms of the occupations in the carbon isotopes. And of course, we can again look at sort of what were called out as the halo nuclei. So if you go from carbon-14 to carbon-15, you're taking your sort of closed shell carbon-14, putting another neutron into the 1s1/2 orbital. Again, pretty much what you would expect for a halo nucleus. And if you look at the calculated radii, again, you see a pretty good jump between carbon-14 and carbon-15, again, as you would expect. Now, if you look at going from carbon-18 to carbon-19, things are a little bit fuzzier. So as you go from carbon-18 to carbon-19, all of the extra particle seems to be going into the 0d5 halves. Now, if I ignore the carbon-18 and I just looked at the carbon-19, it looks like I have filled p shell and 4 neutrons in the d5 halves, they're probably paired together, great. Then you have one extra particle sitting up in a 1s a half. So that would be sort of, yeah, kind of looks halo-ish from a shell model sort of picture, except the core is not the calculated carbon-18. It's some other 18 particle structure, or at least that's what this is suggesting. Now, there's a caveat here. These results are, for the carbon isotopes, are very preliminary. The highest Nmax I was able to go within the amount of time I had was Nmax 8. And so they're not exactly converged results. And in carbon-18, there is a intruder state that is coming down rapidly in energy at Nmax 8. It's still at about 10 MeV, but since it's converging down so rapidly, patterns suggest that it will not become the ground state like in beryllium-12, but it may come low enough energy to actually have a significant impact on the structure of carbon-18. It's hard to say at this point. So I would take any of the results for the carbon isotopes with a fairly large grain of salt, just because it is a low Nmax calculation. Okay, so that's sort of the single particle picture. Now I'm going to change gears a little bit and talk about more of the Elliott SU3 picture where you're sort of assuming everything's correlated. So Elliott SU3 model is based around the SU3 symmetry, and the symmetry is labeled by two parameters, lambda and mu, which can be approximately related to the deformation parameters beta and gamma. Approximate in that if you had large enough values of lambda and mu, then there's a quote-unquote contraction limit in which it's exact. These are light nuclei, lambda and mu aren't that large, so it's very fuzzy approximate. But it does sort of give you a sort of intuitive picture to kind of map onto in terms of what we're seeing. So for beryllium-10, there's different SU3 symmetries that show up in your h bar omega n excitation equals 0 space, and in your nx equals 2 space. And what's shown here, these are sort of your beta gamma plots, where along this bottom axis, where gamma equals 0, you would have a prolate shape. If you went all the way up to the maximum gamma at 60, you would have an oblate shape, and sort of maximal triaxiality happens at around gamma equals 30. And these different points show sort of what the associated beta and gamma are with different SU3 symmetries. So in the Elliott model, you start with sort of the picture of sort of a spherical picture where you have a H0, which is some sort of monopole term, be it your harmonic oscillator Hamiltonian or Wood-Saxon or whatever. But then you expect that there's another term which favors highly deformed states. And so Q dot Q goes roughly like beta squared, which is roughly like some linear combination of lambda and mu. So you'd expect for large values of lambda and mu, you'd expect those states to be lowest in energy. This shows up in the shell model in that each particle in a harmonic oscillator state has definite SU3 symmetry, where the symmetry is N0, where N is just the N of the oscillator shell. And then if you couple all the particles within a given shell, anti-symmetry will enforce that you have a particular spin associated with that shell. And then you get the total symmetry associated with a given configuration by coupling particles across shells up to good proton spin and lambda mu proton, and good neutron spin and lambda mu neutron. Couple those together, you get total lambda and mu and spin. So in this sort of picture, you have both good proton and neutron quantum numbers as well as total quantum numbers. So if I take beryllium-10 calculations and I look at projections of the wave functions onto the different possible symmetry subspaces that you can get in this, so for beryllium-10, what's shown here is the probability of the projection onto the different subspaces. The only subspaces shown are ones where it contributes at least 0.01%. This is representing only about 0.001% of the basis. But as you can see here, for the ground state in beryllium-10, there's a fairly large contribution coming from this particular set of lambda, mu, and spin, and another slightly smaller contribution from this set. But of course it's fragmented, and so you can look at the sort of probabilities associated with the different shapes. And so the size of the symbol in these plots is corresponding to the probability of the projection of the wave function onto a given subspace. So for beryllium-10, you've got the largest projection is onto this lambda mu 22, which is maximally triaxial. And you also have a smaller contribution. I'm not actually sure why this is blue. This should have been red. The blue shapes indicate spin proton. Oh, its spin proton equals 0. And the red symbols is spin proton equals 1. And so what you have is sort of maximally triaxial from the large probability in beryllium-10 with some sort of prolate-ish looking shape. And so when you're looking at the Nielsen model picture for beryllium-10, Nielsen model assumes axial symmetry, and it's not. And so that could be some of the reason why we're seeing some issues in terms of the Nielsen picture for the beryllium-10 occupations. Beryllium-11, you again have somewhat triaxial shape, and the second contribution is a more prolate-looking shape. And in beryllium-12, you've got fairly large deformation, all of it fairly prolate. These up here correspond to what would be the unmixed beryllium-12 intruder state, and this is coming from that mixing down here. I can also play the same game with the carbon isotopes. So this is just a subset of them. In carbon-15, you actually have similarly a very triaxial-ish shape with actually very similar quantum numbers to what we saw in the beryllium-10. Except here, the red symbols, its spin proton equals 1, which is an indication that perhaps my 3 alpha cluster picture is breaking down. Same thing in carbon-16, you have similar to what you saw, sort of slightly triaxial towards the prolate side, and then a handful of other probabilities around roughly the same beta. And again in carbon-17. And you see sort of similar sort of thing happen in carbon-18 and 19. In carbon-18, you sort of see that the SU3 picture is sort of breaking down because you have lots of different spots on these plots. They're all at kind of roughly the same deformation for the spin proton equals 0 and the spin proton equals 1. And this is somewhat consistent if instead of using the spherical SU3 picture, if I'd used a deformed SU3 picture. But again, you're starting to see this sort of alpha cluster picture breaking down because you have this sort of increasing number of proton spin equals 1. So here you have in carbon-19, you've sort of moved past sort of maximally triaxial, moving into more oblate, and carbon-20 is fairly oblate in terms of its distribution of SU3 shapes. Okay, just to summarize, so the deformed single particle picture, sort of Nielsen model-like picture, provides a simple approximate description for the light neutron-rich nuclei. I say approximate because we saw some examples where it kind of didn't quite work. So when you have intruder states, particularly intruder states with mixing, things kind of break down. If you've got a lot of triaxiality, you have to be a little bit cautious. But it does sort of highlight the importance of incorporating deformation into your theory, which we're going to hear next, a nice talk about deformed coupled cluster, which is basically taking this idea and implementing into the coupled cluster model. We saw in the results that there was a bit of a breakdown of the n=8 shell closure in beryllium-12, but we did not see a breakdown in carbon-14. In fact, it looks very much like there's a shell closure there in terms of the occupations. We also didn't see the n=6 or n=14 subshell closure, but I didn't really talk about that much. The occupations are hinting that the core of the 19 carbon halo might not be quite the ground state carbon-18 state, but again, keep in mind these are very low Nmax calculations. So keep in mind that could change significantly as we go up in Nmax. The SU3 picture suggests that beryllium-10 and the carbon isotopes are fairly triaxial in nature, at least for the lighter carbon isotopes. And that doesn't come out of the Nielsen picture, so that's another place where there's a little bit of difference between the two sort of simple pictures. And the spin decompositions, or the spin proton decompositions specifically, are indicating that there may be a breakdown of the 3 alpha cluster structure in the carbon isotopes. Thank you.
So thank you very much, Anna, for the nice talk. Questions? Carlos and then Takashi. Oh, I can't speak. Otherwise, the swap is also okay. Carlos.
Just a curiosity, what's the relation between your occupation numbers and spectroscopic factors?
Depends on how they model the spectroscopic factors. If the single particle orbitals are in fact similar enough, they should be pretty much the same thing. It's a rough way of getting at spectroscopic factors.
I would guess so, yeah.
Then Takashi.
Thank you for a nice talk. I'm interested in this carbon isotope, carbon-19 especially. And then you showed that the carbon-14 to carbon-15 have a raise of the radius, but not for carbon-18 to carbon-19. Why is that? You have some reason?
Yeah. So a couple things could be going on here. Like I said, these are low Nmax calculations, and that there could be intruder states that will eventually come in. And when you have it mixing with intruder states, you will see a large increase in the radius relative to the sort of shell model picture. It could be that it's not converged, although these results are suggesting that it's converging pretty rapidly, even at low Nmax. Aside from that, I don't have a good explanation for why there's not much
May I
of a
just
jump.
ask one more question? So you use a shell model basically. So I mean the harmonic oscillator base. Then how can you estimate the halo property?
That would involve lots of calculations of things I don't currently calculate. I don't have a good way of estimating right now.
Okay.
Right.
Okay, I see. Really? Okay, thank you.
So since we are, Takashi asked something, can we go back to the problem of yesterday of your carbon-22?
Yes.
So, and a question to you would be, do you have any plan in the future to look into that? Is it going to stretch the method? The question there is, what is the core of that carbon-22?
Yeah. In my case, the core of carbon-20, carbon-22, you didn't go further to carbon-22, but I'm interested in what is the core of carbon-22 actually. So maybe I would like to ask you to calculate also carbon-22.
Yes, exactly.
Can I calculate it? Yes. Will I trust it? Depends on how well my observables converge.
Okay.
But maybe something to give a try.
I didn't realize carbon-22 was of interest, or I would have calculated it for this.
Yeah. Okay, are there more questions? Yes, sorry, I didn't see you. Liv Palm.
Yeah, thank you. I've got a follow-up question about, like, how does your picture, like, with occupation translate to spectroscopic factors? Let's say, for example, carbon-17, there are, like, 3 bound states. And, like, let's say that your carbon-16 cores, like, deform, like, 0 plus, 2 plus state. Let's say, at leading order, it's, like, perfectly a rigid rotor. And, like, people, like, doing transfer reaction was saying that, depending on the state at which you were looking at, the core admixture could be more or less different, more 2 plus, more in the 2 plus configuration or more in the 0 plus configuration. And so I was wondering if you could, like, with your method, give us like a way to access this information and, to distinguish which state is more in a given configuration than another.
I mean, yeah, this is sort of the poor man's way of getting at sort of the spectroscopic information. I am capable, though it takes more effort to actually just calculate the spectroscopic factors and look at what states it projects onto. So it is very doable. I just haven't looked at it.
And maybe like a follow-up question on my question is like in carbon-17, like there is a 1/2 plus bound state, which is kind of halo-like according to some calculations that some other people have done. And like how does it like, I don't know if you have looked at it, but like how does it show up like in your calculation? You know, like 1/2 plus state, bound state, very low binding energy that has a halo-like type of behavior. And so I was wondering if you could see that too.
Possible. I haven't looked at any of the excited states yet. These are very preliminary results.
Okay.
But certainly something to look at.
Thank you.
Okay, and I have a question also. So you showed the results mostly with this Dijon potential. Do you think if you change the interaction, you would come to the same conclusion in terms of this occupation numbers, etc., deformation? Or will it be interaction dependent?
I imagine that there's some interaction dependency for two reasons. One, because it's a particularly soft, it's been SRG evolved, and so it's almost more of a shell model-ish interaction than perhaps like the Norfolk interactions that Sayori is using. So I would expect a single particle picture to come out a little bit more nicely for this interaction. The other issue is convergence. And to be able to actually say I'm getting the same picture with both interactions would require me to go up to very, very, very large model spaces to be able to say when it's interaction or when it's calculation dependent. And we currently cannot do that for these isotopes. Perhaps you could look at helium-4 or helium-5 and be able to do a better comparison.
Okay, thank you very much. So let's thank Anna again. And now we go for the coffee break and